Hello, welcome back to my channel. Today I'm going to cover a very simple subject. I'm going to talk about outputting to screen RAM on a Commodore 64. I've written a very simple program. All it really does is cycle through every symbol and every colour until we've written 255 symbols onto the screen, and they'll all appear in different colours. Now, this just consists of a loop. We're going to use the X register to cycle through the values we want to store on the screen and the colours. And you can see here it's very simple. We start by initialising the border colour and the background colour. So that's address D020 for the border colour and D021 for the background colour. We're going to do this by just loading the accumulator with 0 and storing it in there. And all we're going to then do is just increment X until we've written 255. The value of X will increment every time the loop is run. And this means that because we're using X as a pointer, we will not only change what's written at that location in screen RAM or colour RAM, but we'll also increment where we're storing to each iteration as well. So if we start at 0, we're starting it relative to address 400, and then as we increment X, we're storing a higher value at location 401, then 402, so on and so forth. And the same with the colour RAM also. So we are writing to screen RAM and we're writing to colour RAM. And then when we get to 255, we stop. That's all it does. So here I have Retro Debugger open, and you can see it kind of does work. There is a bit of a problem though, and I think you can spot what that is. We've got 16 colours to play with on the Commodore 64, and the problem we've got here is we start off on 0. So that happens to be the same colour as the background. So anything you write, if it's the same colour as your background colour, it's basically not going to display on screen. So although this looks nice, it isn't great, and I think we need to improve that a little bit. So this is what we end up with. This is the improved version, and you can see it's actually hasn't got any blackness, apart from I think this one symbol is meant to be some kind of transparent symbol. I don't know what it's meant to look like. But I had to write a bit of extra code to ensure that if we were the same as the background colour, then we didn't really want to be having that colour. We want to increment by 1 to ensure that it's cycled. Whereas you can see, this looks a lot better, and we've got all this, apart from that one, which I think is not meant to be there, we've got all the symbols appearing now, and you can read all of them. Like most things, when I do these videos, I think I'm going to be done in a short space of time, and this was actually a lot more difficult than I thought it was going to be. When I first wrote the code, it compiled and ran. It wasn't incrementing properly. It wasn't getting rid of the black space. I couldn't really figure out what was going wrong. I realised eventually, when I referred to the documentation that talks about the various memory addresses, that if you store a value in a location such as D020 or D021, not all of the bits are written to. If you attempt to write code that pulls a value out of there and compares it, it's going to fail, because I found that I was setting D021 to 0. Here's the problem we've got. If we view addresses D020 and D021 in Retro Debugger, you can actually see that they're set to F0 and F0, despite the fact I told the program to store 0 in there. So the problem we have is that when you do this, it only writes to the first 3 bits, which I didn't realise. So I could see the 0 going in, but I couldn't figure out why I was getting F0. I would never have realised where my code was going wrong, because I was comparing to a value of 0, and what D020 held and D021 held was F0. So that was never going to work. So for this reason, I've defined a single variable, and that's going to be used to mask out the unwanted part of that calculation, because we don't want to look at the F, we just want to look at the 0. So that's what this colour mask variable is doing. This program starts by loading 0 into the border colour and the background colour, which will make it black. And then it goes straight into a loop, and the first thing it will do, before we write anything to the screen, we will check to see if we are in danger of writing to the screen something that's the same colour as the background. And so we're going to jump straight into this manage colour routine. So the first thing we do, and this is where my program, it took me a long time to figure this out, get my program working correctly. We're going to grab whatever's in D021, and originally what I had was code that did a comparison and that didn't work. So what we're going to do is mask out the highest value 4 bits. We do this by taking whatever value is the current background color that we've set, which will actually start off at 0. This AND command will effectively say we want to ignore the first 4 bits. Whatever remains will be stored in this variable color mask. Because we're setting these 4 bits to 0, we will never have anything in the result that occupies the first 4 bits. So we've applied a mask to it. So next thing we do, we're using the Y register to increment the color. So the difference between this program and the last program is that everything ran off of X register. This time I felt I couldn't do that. I needed to use Y. So we can use X for the screen position and Y for the color. And the first thing we'll do is we'll grab whatever Y happens to be set to at the moment. We're going to start off at 0. The first thing we'll do is we'll compare it to what's in this color mask variable, which we've stripped the highest 4 bits out of. And then we're going to do some branching. So, you know, if we find that there is no clash, we'll do something, and if there is a clash, we'll do something else to mitigate that. If they are the same, we'll jump down to here. All we do is we increment the Y register. You know, we start off at 0, which happens to be the background color. It'll straight away increment that and make sure we're never outputting black to the background color. If there is no clash, we will store whatever color is in the Y register, and we will write that at position X. So again, X is controlling where on the screen we're writing this, and Y is the value. This is also something, in fact this is wrong. I actually got this wrong when I first did this because I was trying to output Y to the color RAM. That should actually say X. Little mistake there, but yeah, we're all human. When I first ran the code, I had a mistake in there. I was storing with reference to Y, so of course what it did was it didn't increment the color after the first 15 iterations, which was a bit silly. And then the next thing we do, in the old program, you could keep on incrementing that border color to your heart's content, and what it would do, it would wrap over once it got to, I suppose, 255. We can't really repeat that trick here. So what I decided to do is limit the Y register to a value of 15. So if we've gone for our 15 colors, we need to wrap back around to 0. So if we haven't reached 15 yet, then we'll increment Y so that the next time we run this bit of code, we will be on the next color. It just loops back to the beginning of the program again, and then this command here actually writes something out to the screen. So that's saying, again, 0400 with respect to X. So effectively what we're doing is saying if X is at 0, we're going to be at location 0400. If X is at 1, we're going to be at location 0401, 0402, and so on and so forth. But because, like with the earlier program, this is in fact not changed from the earlier program, whatever is contained in X will also be written there. And that's how you end up with this. You might be thinking that this code is a little bit more complicated than it really needed to be. Why are we interested in comparing what the background color is? I could have just set it to 0, for instance, and said compared to 0. Should have made things a bit easier for me. Well, the reason for this is that I decided to make the code somewhat scalable so that if I wanted to change the color of the background, it would mean I wouldn't need any further modification to the code. So I'm not explicitly checking that the background is black. The code is checking that we're not the same as the background color. So I can change this to a completely different color and we should find that it still works. And here we are. I changed the background color to 3, I believe it was. And yeah, you can see it's kind of working the same. There's nothing that is the same color, although some of these don't render too well, I must admit. I think black is a better choice. But yeah, just to show that it can be done. And that's basically it for this video. So yeah, have a nice weekend. Thanks. Bye.